Lesson 55 of our no-nonsense A-level physics lessons, all about explosions. Now, explosions are situations where momentum is conserved. This is an interaction between two bodies where momentum is conserved, but the kinetic energy after the interaction is more than it was before. So explosions increase energy in the kinetic energy store. So increase kinetic energy. And you can do that energy, I think I spelled that right. You can do that by moving energy from the chemical energy store into the kinetic energy store, in the case of a chemical explosion. Or you could do it with springs, can cause things to explode away. It doesn't matter. You can have more than just two bodies in our closed system, but it's easier to analyze if we consider just two bodies. You can have explosion where lots of bits of shrapnel fly all over the place. In all of those cases, momentum is still conserved. So there's an increase in kinetic energy, but the energy is conserved. Energy is conserved, still just not kinetic energy. And momentum is conserved. Remember, this is still classical physics. No accelerated expansion of the universe here. So what does that mean then? How do explosions work? Well, we still have ma ua plus mb ub is equal to ma va plus mb vb. That is still true. But let's take the simplest case. Let's take the case where the initial velocity of both parts is 0. Now, if it's not 0, let's say you're doing an explosion calculation, but the original two objects that are initially together are moving, then all you have to do is subtract that initial velocity from all of your velocities. In other words, you shift your reference frame. And in classical physics, you do that with Galilean transformations. You just subtract that initial velocity from every velocity measurement, and it gives you your answer. So let's take the case where UA and UB is 0. So then we've got the before times and the after times. So let's draw a quick diagram. We've got two objects which are in contact with each other before, and then something happens and they're going to move apart. So there's our two objects in the before times, and our two objects in the after times over here are going to be, oopsie, can I undo that? Does it allow me to undo the making it slightly larger? Yes, it does. Let's move this over there. They're moving apart. Okay, initial velocity is 0 for this. So let's put down here ma, mb. That's the masses of these bodies, mb. And let's have it so that ua is equal to 0 and ub is equal to 0. Well, in that case, we're going to get our velocities like this. And I don't know what they are relative to each other because it depends on the masses. Like that. So in the picture I've just drawn here, MB is obviously greater than MA. This is our VA, this is our VB. And you will notice that they are in opposite directions. VA and VB are in opposite directions. So we could say that 0, the initial momentum, is equal to MA VA plus MB VB, but that's only if we consider our velocities as vectors. And remember that exam boards are very bad at doing that, so you might have to put a minus sign in for VA because it's going to the left. What does that mean? That means that the magnitude of MA VA is equal to the magnitude of mb vb. And that is true for explosions. Now, as I've said, if the initial velocity of the object was ma and mb stuck together, if the initial velocity of those was not 0, then we would have to add this extra bit of velocity onto, or subtract the extra velocity, should I say, from all of these UAs, UBs, VAs, and VBs to get UA and UB to be 0. But there we go. That's basically it for explosions. And we don't need to spend any more time on it than that. If we're working in terms of vectors, then what I've just written would be written as MA VA is equal to minus MB VB, like that. And that's absolutely true, but I'll just be so careful with the signs and whether or not we're working with vectors or scalars. That's it. I don't know what else you want me to say. That's it for explosions. It didn't take much time. So energy changes take place, moving energy into the kinetic energy store to increase it. We still can say that energy is conserved. We can still say momentum is conserved. That's true. We can say that the bodies are moving apart with different velocities if the masses are different, and the ratio of those velocities is going to be the reciprocal of the ratio of those masses. That comes out of that equation there, or should I say the ratio of the speeds comes out of that equation there. I suppose we could drag this out a little bit and say that VB would be equal to, I don't want the minus sign. Let's do this as scalars. So I could say that the VB speed is going to be MA over MB multiplied by VA. And we could do it the other way around for VB, just like that. But yeah, we're just treading water now and saying the same thing in different ways. That leads to that. Okay, I'll stop there. That's it. We don't need much notes on explosions. We just need to practice doing calculations to calculate what the total kinetic energy after a collision is, which will just use half mv squared for both bodies, and that will tell you how much energy has been removed from whatever the energy store was that the energy came out of. Short and sweet. Well, that actually brings us to the end of dynamics, and I hope that you found that useful. Next lesson, we'll be moving on to work, energy, and power. I hope I'll see you then.